I do want to express my appreciation for receiving this award. I value it very highly. My interest in science has lasted for very many years. I started as a student to become interested in the subject, and after I retired in 1981, I decided I would devote much more of my time to that particular topic, and it's very pleasant to realize that something that one does in this way is appreciated. Secondly, I must apologize for the fact that it's not possible for me to be present in person at your meeting. My home circumstances make it difficult nowadays for me to be away from home overnight. I thought it would be useful to talk a little about the careers of two well-known scientists, Neville Vincent Sidgwick and Henry Eyring, an Englishman and an American. My reason for choosing them is partly that they offer a tremendous contrast in the way they did their science. And all my reading of science has led me to the conclusion that there really is no such thing as a scientific method. People sometimes talk about the scientific method, but it seems to me that there are as many scientific methods as there are scientists, and that every problem has to be treated in a different way. And at the same time, I conclude that it's very difficult to plan a piece of pure scientific research. It may be more possible, it is more possible in applied science, but in pure science it's almost impossible to plan, and because it's so difficult to see ahead. And it would be like asking an explorer going into a new territory to draw a map ahead of time of the territory. Obviously that cannot be done. We must make our decisions very continuously as we do the research. Another conclusion I've come to is that there's really no special breed of person who becomes a scientist. Many people who became very good scientists initially intended to do something quite different. Henry Eyring is a good example. He intended to be a mining engineer at first. Both Dirac and J.J. Thomson, who became physicists, of course, they both started as engineers. Some people have started as scientists and then have become, I beg your pardon, as lawyers and then have become scientists. William Grove is a good example of that. He became a barrister, a lawyer, practiced as such, and then became a professor of chemistry, did some very distinguished work, invented the fuel cell more than 150 years ago, and later went back to the law and became a judge. And of course there are a few people who have become quite famous for work that they did quite in fields outside science altogether. Four of them come to my mind. Sir Christopher Wren, whom we all remember as a great architect, was a professor of mathematics and was very well versed in mechanics and astronomy. Benjamin Franklin is an obvious example, a very great statesman, one of the signers of the Declaration of Independence, who of course is famous for his pioneering work in electricity. The composer Alexander Borodin, Russian composer, he was a full-time professor of chemistry, and it's said that he only composed music when he didn't feel very well, so that his musical friends were in the habit of greeting him by saying, "Good morning, Professor Borodin, I hope you don't feel too well today." And finally, Chaim Weizmann, a very interesting case. He was the first president of the State of Israel, and but he began his career as a chemist, an organic chemist, and was a very good one, made very important contributions of practical importance, and it was partly because of the chemical work that he did that the British government decided to convert its mandate of Israel into the State of Israel, and it was for that reason that he became the first president. Now, as to the characters of scientists, some scientists, like other people, are generous people, some are just the opposite. There are a few scoundrels in science, just as there are in all fields. There may not be as many scoundrels in science as in other fields, perhaps because scoundrels always get caught out fairly soon. And religious belief, I think, is a very interesting topic to consider. Some scientists are very religious. Henry Eyring, a good example of that. He was a Mormon and became an important figure in the Mormon Church. Michael Faraday and many others, Clerk Maxwell, were religious men. Sidgwick, on the other hand, was a rather militant atheist. So that there seems no correlation between religious belief and scientific ability. Gregariousness is another interesting topic to consider. Some scientists are very friendly, gregarious people. Others are quite the opposite. Röntgen, who discovered X-rays, is believed never to have discussed his science with any other person, not even with the assistant who helped him with the experiments. And when Röntgen went to get his Nobel Prize, he received his prize and was supposed to give a lecture afterwards, but when they looked for him to give the lecture, they discovered that he'd gone home. Oliver Heaviside, who first thought of the Heaviside layer, he was very much a recluse, a hermit. He probably holds the record for early retirement. He retired from his job as a telegraph engineer at the age of 24, and then went into seclusion, hardly ever spoke to anybody. But fortunately, he did communicate by letter and by writing articles, and so we do know a lot about his work. Now, when we come to consider Sidgwick and Eyring, we can at once say that they differed tremendously in the way they did their science. Sidgwick knew very little mathematics and didn't make much use of it, but he did understand in a general way what the mathematics of science was all about, and he applied it to a vast amount of chemical knowledge. He was a great chemical scholar in the sense that he read the literature. He probably read every paper that was written in his time, which was possible, not possible today, of course. And he was very well informed about what had been done in chemistry, and his great contribution was to apply the ideas that he got from other people, mathematical ideas, apply them to the vast body of chemical knowledge. Henry Eyring was just the opposite. He wasn't well versed in scientific literature. He didn't bother very much about it. He left that to his students to read the literature. He worked intuitively. He had all sorts of excellent ideas which he discussed freely with students, and very often we told him that things had been done already, or things were obviously wrong, and so on, and he proceeded in that way, quite differently. And of course, his knowledge of mathematics was considerable. Now, I'll say a little bit first about Sidgwick and his career. I have a picture here which shows him much as he was when I was a student and took his lectures. And there's another picture of him that's quite similar that appeared in the front of his famous book, The Covalent Link in Chemistry, which shows him at about the same age, about 60 or perhaps a little less. He was born in 1873, and he had a very distinguished family, in the sense that his father was a classical scholar, and he had three uncles who were very famous in their time. One was Henry Sidgwick, who was professor of philosophy at Cambridge. Another was Benjamin Brodie, who was professor of chemistry at Oxford. And the third was Edward White Benson, who later became Archbishop of Canterbury. And this is a little amusing in a way, because Sidgwick himself and his father and two of his uncles at least, Henry Sidgwick and Benjamin Brodie, were very militant atheists. And the Archbishop Benson may have felt a little uneasy in their company. Perhaps I could say a word about how I first happened to get in touch with Sidgwick. In 1933, when I was at school in England, I decided that I wanted to go to a university and do chemistry. And so naturally I went to my chemistry teacher and asked him for advice as to where to go. And since he was an Oxford man, he suggested that Oxford was probably the best place for me to go, which in fact was, I think, true at the time. Oxford was a very distinguished university for chemistry at that time. Robert Robinson was professor of organic chemistry, Sidgwick was there, and there were several other people, including Hinshelwood, with whom I ultimately did work. Now my teacher told me that Sidgwick, he thought, was the most brilliant chemist in Oxford, so that I should apply to go to his college, Lincoln College, which I did. But then I had to give a second choice, and my teacher said, well, there was a very brilliant young man by the name of Hinshelwood who was doing very good work, and he suggested that I should put him down as my second choice, which I did. And Hinshelwood was at Trinity College. Now, in December of 1933, I went down to Oxford and took the scholarship examination for admission. And I still remember, after so many years, that while I was doing the experimental part of the examination, there was an experimental part in which we had to solve some problem. I don't remember what it was. I remember at the time Hinshelwood came up to me and in his inimitable drawl, which I will now imitate, said something like, well, Ladler, how are you getting on? And I said, well, I thought I was doing all right, thank you. And a few days later, I did in fact get a letter from Hinshelwood offering me a scholarship at his college, Trinity College. So that I got my second choice, not my first choice, which is significant, and I'll refer to that again later. As a result of that, then soon afterwards, I was sitting at the feet of Sidgwick, amongst other people, listening to his splendid lectures on inorganic chemistry, in which he was explaining inorganic chemistry in quite an extraordinary way, and giving us a deep insight into the subject. Now, Sidgwick himself went to Oxford, as his father had done. His father, in fact, was a teacher at Oxford. Sidgwick went to Oxford and got a first-class degree in science, chemistry, and But when the members of his family knew about this, they heard about this, they weren't very impressed, because in those days science wasn't highly regarded. Classics was considered most important, and some of them rather sneered at the fact that his degree was in science and not in classics. So Sidgwick did a rather unusual thing. He went back to Oxford for 2 years and took a degree in classics, Latin and Greek and ancient literature, and again got a first-class degree. So then he felt satisfied that the family honour had been restored. Now, afterwards, after that, he went to Tübingen and took his PhD. It wasn't common in those days for English scientists to go to German universities, but it was quite common for American scientists at that time to do so. But Sidgwick went to Tübingen, got his degree, and on his return in 1901, he was elected a fellow and tutor of Lincoln College. And since he never married, he resided at the college from 1901 to 1952, when he died. Now, he was unusual. Sidgwick was unusual in that he was a late developer in science. Many scientists do their best work in their 20s and 30s, but Sidgwick was well into his 40s before he did anything of much importance. And his work was at first in organic chemistry. He was a member of the organic chemistry department, and the professor of organic chemistry in his time was Sir William Perkin, the son of another Sir William Perkin, who was famous for his work on dyes. And Sidgwick used to say later that Perkin was fond of saying about physical chemistry that physical chemistry is all very well, but of course it doesn't apply to organic compounds. A rather devastating remark, after all, because organic compounds do comprise a vast proportion of chemical compounds. And so Sidgwick's relationships were a little uneasy with Perkin, but in 1914 he happened to be on a boat going to Australia, and he ran into Rutherford, who had already made a great name, of course, for his work on the atomic nucleus. And Rutherford suggested to Sidgwick that it might be a useful thing to do to consider some of these new theories, the quantum theory and so on, consider these new theories and explain some of chemistry in the light of these theories. And this was quite an original idea at the time. Just previous to that, of course, in 1913, Niels Bohr, in Rutherford's laboratory, had done his work on the hydrogen atom, and that, of course, revealed that there was a possibility of explaining chemical facts in terms of theory. And Rutherford's idea was that Sidgwick should devote his career to that, and Sidgwick took this up with some enthusiasm, and in fact that was his life's work. A few years later, 1919, before Sidgwick had done much of any importance, he did apply for the professorship of chemistry at Oxford, but he was turned down, not surprisingly, because he hadn't done very much. He was turned down in favor of Frederick Soddy. Now, Soddy had worked with Rutherford and had done some very important work on isotopes, but he was an early developer and did very little in his later life. And when I was an undergraduate, in fact, I went to Soddy's lectures. They were very dull, and at that time Soddy was doing nothing but giving the necessary number of lectures and then going home. He worked on economic theory, but he'd really lost his interest in science. So that it would have been much better for Oxford if they had, in fact, appointed Sidgwick instead of Soddy, but they were not to know that because Sidgwick's work had been rather undistinguished. But by 1927, Sidgwick had made very great progress, and in that year appeared his famous book called The Electronic Theory of Valency. And in that he made much reference, of course, to the work of G.N. Lewis, who was a great pioneer and should have got a Nobel Prize for his work, but somehow didn't. And Irving Langmuir, of course, had worked along similar lines, but Sidgwick extended what they had done. They had the ideas very well, but Sidgwick extended them greatly into the whole area of organic chemistry and particularly inorganic chemistry, and that was the great contribution he made throughout his life. In 1931, an important change, there was an important change in Sidgwick's life. He was invited to be the George Fisher Baker Lecturer at Cornell University. And this was his first trip to the United States. He was in his late 50s at the time, and since he was a rather prejudiced type of person, his immediate reaction was, I'm not going to like that place when I get there. But the interesting thing is that a week or so after he had arrived in the United States, he had settled down beautifully. He loved it and got on much better with students in Cornell than he had done with his own students. His own students had been rather in awe of him. He was a rather formidable person, but the Cornell students treated him in quite a friendly way. They even called him Grandpa, which delighted him. And so he got along very well, and the students, in fact, invited him to stay at Telluride House, the student residence. And after that, he returned many times to the United States. Many times went back to Telluride House, and he became the best known, probably the best known chemist in the United States. It was a proud boast of his that he'd visited 46 of the 48 continental states. I can't help mentioning that I myself actually have visited all 48. The last one I visited about 30 odd years ago was Maine, rather surprisingly. Well, when he returned from Cornell, Sidgwick continued his work on the electronic theory of valency, expanded it, and finally, much later, in 1950, came out his great book called The Chemical Elements and Their Compounds. A vast book, 2 large volumes, a total of over 1,700 pages, a total of 750,000 words. He was aged 77 when the book came out, and this, of course, had been his life's work for the previous 25 years or more, and it was considered to be a great contribution to learning, to the world of science, because for the first time it explained the facts of inorganic chemistry in a rational way. Now, Sidgwick was had an odd personality. He was not an altogether likable person, I'm afraid. He had many prejudices. He would overcome the prejudices if need be, and we saw that he did so about the United States, but he had a very acid tongue and made quite a few enemies because he tended to trip people up and so on. One of his former students, Leslie Sutton, made a very interesting comment about him. He said, in personal judgments, Sidgwick seemed sometimes to be carried away by the poetic ecstasy of imaginative denigration. Denigration. In other words, he seemed to want to run everybody else down, but nevertheless he had many friends and also many enemies. In 1951, he decided that he would make his last visit to the United States and had to have an operation, in fact, in order to do so. And he visited Cornell again, stayed at Telluride House, but he was very frail and had to be helped with walking. And the students were very good and took him on trips to see the fall colors. But on the ship home, he had a stroke and he died early in 1952. Well, now I come to Henry Eyring, a very different character altogether. And again, may I tell a little story about my own experience, how I came to work with Henry Eyring. I was working, doing some research with Hinshelwood in kinetics, and Hinshelwood always believed that one should broaden one's experience. So when I decided to apply for a fellowship to go to an American university in 1937, I consulted Hinshelwood, and his suggestion was that I should work with Linus Pauling as being a very eminent chemist, and of course he had done very important work just before that. So I put down as my first choice Linus Pauling. But I also had to put down a second choice, and it happened that just previously Henry Eyring had visited Oxford and had given a seminar, and I well remember that seminar because of an incident that occurred after it. The professor of physics was Professor Lindemann, a rather unpleasant man, and after Henry Eyring finished his lecture, Lindemann got up and in a most offensive way criticized Henry Eyring's work, ridiculed the theory, cross-examined him as to his basic knowledge of physics, and so on. It was all rather embarrassing to the audience, and I remember that afterwards Hinshelwood was very angry with Lindemann for having treated a distinguished visitor in such a way. Hinshelwood and I were very well aware then of Eyring's work. We were very impressed by it. We made use of it in some of the research that we had done. So I put down Eyring as my second choice, again, second choice. And I had to be interviewed for the fellowship, and the chairman of the committee told me at the interview that they had decided to give me a fellowship, but would I mind working with Eyring and not with Pauling, because so many Englishmen had been going to work with Pauling, and they thought perhaps I would like to work with Eyring. Well, of course, I was delighted to do so, and I've never regretted the fact that I did work with Henry Eyring. So it's rather interesting that I got my second choices with Hinshelwood first and then Henry Eyring, both of them second choices. I might have worked with Pauling first with Sidgwick and then with Pauling, which would have meant I'd probably have done my research in a different field, and I have a suspicion I wouldn't have been very good at that. I mention this just to emphasize the great importance of luck in all our lives. I think we have to admit that sometimes luck is on our side, sometimes it's not. I was, I think, lucky in that I did get my second choices in those cases, because my subsequent career was determined by those two people with whom I worked. Henry Eyring was born in 1901 in Colonia Juarez in Mexico. Here's a picture of Henry Eyring, much as he was when I worked with him. He went to the he first intended to be a mining engineer and took his first degree in mining engineering, but then he went to the University of California and did physical chemistry. And And his first job was at the University of Wisconsin. And he always used to enjoy telling us as graduate students that he'd been fired from the University of Wisconsin, and telling us how it came about. The chairman and head of the department, the chemistry department, in his time was J. Howard Matthews, who was quite a distinguished university figure and remained head of the department for many years. And Henry Eyring was assigned to teach a laboratory course. He wouldn't have done it very well, I'm afraid, but that was what he was assigned to do. And Matthews told him that his first job was to paint the floor of the laboratory. Henry was a little surprised at this, but did it, and Matthews came round and looked at the floor and said, well, he thought it would perhaps do for a first coat. So Henry had to put another coat on. Well, shortly after that, he remarked to a colleague that he didn't like much the way the department was being run. He didn't think the department would ever amount to anything as long as Matthews was around. And an hour later, Matthews, having heard this story, called Henry Eyring in and fired him. In those days, of course, one couldn't grieve. At least if one could grieve, one had to do it by oneself. As it turned out, it was probably, again, good luck for Eyring that this did happen to him, because the next thing was that he went to Berlin to work with Michael Polanyi, and they did their very great work on potential energy surfaces. And soon after his return from Berlin, Henry was appointed professor at Princeton, where he remained for some years, and then later, of course, went to the University of Utah. Incidentally, his trip to Berlin revealed something that he hadn't known. He had assumed that he was an American citizen, but it turned out that officially he was a Mexican. So later he did have to take out naturalization. In 1935, of course, Henry Eyring made his great contribution to developing transition state theory. And much of the rest of his career, of course, was very much concerned with applying transition state theory to various different processes. And when I arrived in 1938, of course, transition state theory had been applied to some processes, but there were still some remaining problems. And so what I did was to work on reactions in solution at first, and reactions on surfaces. And we made a little progress there. Now, a year or so after I arrived at Princeton in 1939, Samuel Glasstone arrived, and here is a picture of Glasstone. Again, he was about 40 years of age when he arrived at Princeton. That shows him, I think, a little older. And Glasstone had had a distinguished career in England as an electrochemist, and he came to work with Eyring at first, and then he was a research associate at Princeton for a short time afterwards. Now, Glasstone had written many very good books, very useful books for students at that time, excellent books, some of which I still have and some of which I still use and find very valuable. And he was, since he was an electrochemist, he was very interested in overvoltage. And so the three of us, Eyring, Glasstone, and I, decided to try to apply transition state theory to overvoltage. And so we formulated that. And sometime before Glasstone had arrived, Eyring had suggested to me that I might like to collaborate with him on writing a book. Eyring himself didn't really like writing very much, and he knew that I did. And so he suggested we write a book. And when Glasstone appeared, he was the obvious person to work with us because he was so experienced. And so we worked on the book that came out in 1941, The Theory of Rate Processes, which was the first book that I think that gave the applications of the theory, that developed the theory in the first place, from first principles and as far as it can be, and applied it to a number of different problems. I well remember during the writing of the book that we had many arguments together, and this, I think, was typical of Aring's way of doing research. We would argue at the blackboard about points of scientific points, always in a very friendly way, of course. And on one particular occasion, something rather amusing happened. We had a big argument about something to do with equilibrium constants and the effect of temperature. And Glasstone and I were on one side of the argument, and Aring was on the other, and we argued all morning, I think, and then we split for lunch, and Glasstone and I had lunch together, and we decided that Aring was right, we were wrong. So we went back to see Aring in the afternoon, and were somewhat disconcerted to find that he had decided that we were right. So we continued the argument on the other side, and eventually got it all resolved. But at any rate, that's a very good way of learning anything, of course, to argue about it, especially with people like Glasstone and Aring. Aring's later career, of course, was at the University of Utah, and he did very distinguished work. He remained extremely active until he was 80 at least. He had a wonderful personality, always full of lots of ideas, some of them wrong, of course, but it was easy to talk him out of the wrong ideas, and he was always very pleasant about arguing about anything at all. So that is essentially the way he proceeded, completely different from Sidgwick. Of course, Sidgwick just was a scholar who did his work for the most part by himself. Aring liked to have people around him arguing with him. I'd like to say a few words about the history of science and the writing of the history of science. I have to give a lot of credit to my tutor Hinshelwood, with whom he was my tutor for 3 years, and then we did research together. This shows him a little older than he was when he was my tutor. He was, I think, 37 when I went to him, and he had done very distinguished work before that on explosions, very pioneering work on the mechanism of explosions, and also on surface reactions. And I think his Nobel Prize that came later must have been based very much on that early pioneering work, because his later work was not as distinguished. He did some good work on bacterial growth. Some of it became controversial, but I think in the end he turned out to be essentially right. And he, I think, helped me greatly in writing and in being interested in the history of science. Because in my time at Oxford, we still had the old-fashioned system of reading essays. We had to write an essay once a week and read it to Hinshelwood. And reading something to Hinshelwood, somebody like that, really keeps one on one's mettle. One has to be very careful, because any mistakes will be spotted, of course. And I remember one amusing incident where I did make a historical mistake in that I referred to the work of William Bone, who was doing work on gas reactions, and I read out that William Bone had done such and such work, and that he'd interpreted his results in terms of free radicals. And Hinshelwood interrupted at that point and said, "Old Bone? Old Bone?" He said, "Old Bone never believed in free radicals." So I learned from that little interruption the importance of getting things right. And that after all, is perhaps one of the first lessons of teaching, of writing about history of science, getting it all right. Now, Sir Peter Medawar made a very interesting statement about writing, which I will slightly change for this purpose, but he said with regard to writing, correctness, cogency, and clarity, these three, but the greatest of these is clarity. Let me say a few words about those topics. Correctness, cogency, and clarity. They're surely of great importance in writing anything, and certainly in writing history. Correctness and cogency, perhaps we can discuss together a little. Lord Macaulay made a very interesting comment, and he certainly knew about the writing of history. Lord Macaulay said, "He who is deficient in the art of selection may, by showing nothing but the truth, produce all the effects of the greatest falsehood." Very interesting comment, I think. In other words, you can say things or write things, each element of which is strictly true, but which as a whole is false. And of course we know that lawyers are famous for doing just that, of course, because they select in a particular way. And politicians, of course, select in a particular way. But of course scientists mustn't do that. We must select in a way that, in such a way that we give the entire truth. And we can select as much as we like, but we must do it with great care. And that, I think, is more or less what one means by cogency. Now, clarity, as far as clarity is concerned, of course one must be as clear about everything as one can be, but there are some pitfalls which I think one should be aware of. I remember when I first started to teach in a university, one of my students made a comment to me. First of all, she said, "Well, we understand your lectures very well," and I thought that was very nice. And then she went on to say, "But now Professor X, we don't understand a word he says, but of course he's very brilliant." Now, it struck me, of course, that here was a judgment being made about someone. The idea seemed to be that because he was brilliant, he wasn't being clear. And I happen to know Professor X, of course. I knew Professor X, and I knew the reason that he didn't lecture well was that he was muddled. He was muddled. And there is really no correlation between clarity and one's ability. So I think it's important for all of us to realize that we must be clear, and it's very important, I think, that the public should not be deluded into thinking that if a book is obscure, it must be a great book. There are one or two books about science which I think are not at all good, which do not give a good idea of what science is all about, but which have been very popular with the public, which have sold very well. But I understand that a lot of the books that have sold are simply gracing people's bookshelves. So that one mustn't always expect clarity to be popular. There is, of course, a great importance, I think, for more and more history of science to be done, because I feel rather strongly that by taking a historical view of science, we can do much better in presenting science to the general public. And I think I think we can all do that. We can all do much more to present science to the general public, which is rather ill-informed about science, especially about the relationship between science and technology. And I think that the historical approach to science is greatly to be recommended for trying to communicate science to the public. Thank you.